have computed the live information, we can use it to construct the interference graph. Recall, the interference graph is used to avoid allocating a register to two variables which are live at the same time. What we do is to go through each vertex again, and we maintain a set called live, which is initialized to the live out of that vertex. Then, when we define a variable, we add an edge. Say we define x, then we add an edge from x to each variable in the live set, except x, if it's there. And obviously, if this edge is already there, we don't add it. So we inspect the instructions in reverse order, starting with the last instruction in a basic block. And when we have considered that instruction, we update the live set to the following. The variables which we used minus, a union with live set minus those which were defined. Okay, so this assumes that there is only one defined variable in each instruction. So, an example. If we have this, the question is, as we saw in the first lecture, how many registers are needed? Well, we start with, we will look at this vertex, and we start with setting the live set to out of it, and that's C and F. Okay, so we define F and make an edge between F and each variable which is live, and that means between F and C, and well, not between F and F. Okay, and then we don't use this yet, because we may want to allocate D, for instance, D and F to the same register if D is not live after this instruction. Okay, so we update the live set, and it becomes C, F, and not F since it was defined there, but C and D and E. Okay, there. And then we define E, so we add an edge between E and each in the live set, except E itself. Okay, so we add these two edges and continue like that. Okay, so when we have created, we go through each vertex and do the same thing for each, and then we have created the complete interference graph. So it is one graph, but we add to this graph, we add edges to it when we visit each vertex. I mean basic block. There are also vertices in this graph, but it's not what I meant. Okay, so how can we color it? Well, without saying how we can do it, but this is one coloring. Can we use only two colors? Not with this interference graph. But there is something called register coalescing, and that the purpose of it is to coalesce or merge two nodes in the interference graph. So C and D, they can be merged into one. Okay, why? Well, they have the same value. And there is no conflict of a later, um, okay, say that one of them, that they would get different values later on and therefore have edges in the interference graph. But due to this assignment, there is not a need to add an edge. Okay, normally we would not do that, but since C is live there and here, we would add this edge, but we don't have to. Since this is a special instruction, a copy instruction with C as the operand. So what we can do is to remove the operand, the source operand, from the copy statement, from the live set, and then add edges between the defined variable and the others in the live set. So well, yeah, we that's exactly what I what I said, namely that we should remove y, I mean the source operand from the live set and add edges to the others in the live set from x. I mean from the variable which is defined. Okay. So summary so far. Copy instructions or move instructions, they are treated in a special way in order to make it possible to merge two variables into the same register. And variables live at the same time, they should not be allocated a register. I mean, we can only put one value in the register. So therefore we have this interference graph with edges to represent this information. Then we want to color this interference graph with as few colors as possible, but we are not looking for the optimal solution always. Of course, it's good if we find an optimal solution which uses so few colors that there are enough register in the machine. But if the optimal coloring uses 300 colors, then there is not much hope of having a machine with 300 colors, 300 registers. Okay. Furthermore, graph coloring for at least 3 colors is NP complete. So we cannot use, I mean, we cannot aim at finding an optimal solution for large interference graphs. What we will use is instead an approximation, a heuristic algorithm, which was invented by the IBM mathematician Greg Chaitin. He was recruited for this project, the first RISC project, because they needed a better register allocator than the somewhat ad hoc which was used before, not only by IBM but by many other compilers as well.